All right, sorry about that. Here we are, maximum and minimum. So the second derivative test, you might think that what you had just been doing this whole time was the second derivative test because the similar thing that we did with the first derivative was called the first derivative test. But it's not actually called the second derivative test until you get to here, which is actually an alternative to the first derivative test for determining local extrema. So it's a way that you would find maximum and minimum values on the graph. F prime of C equals 0, or if F prime of C equals 0, then, sorry, you're looking for a critical point first. So a critical number, and if F double prime exists on the open interval, then F double prime of C being less than 0 means that F of C is a relative maximum. And it means that F double prime being greater than C means that F of C is a relative minimum. Now, personally, I think the second derivative test is really only useful if you're looking at one particular value. Otherwise, I would always use the first derivative test. The reason is, if F double prime of C equals 0, then this test is not going to help you at all, and you have to go back to the first derivative test anyway. But we're going to go through an example of how to use the second derivative test because we will probably find it to be more useful to us when we start looking for extrema later on in this chapter, talking about word problems, mostly just to verify that a value that we found is a maximum or minimum value. So to find local extrema, we're going to verify using the second derivative test if appropriate. First, we're going to take our function f of x. I'm going to give you that function as x over 1 plus x squared. And we'll find the first derivative, and then we'll find the second derivative. First, I'm going to review with you just how to use the first derivative test, and then we'll do it with the second derivative test. So go ahead and find your first derivative. F prime of x is f prime g, so 1 times 1 plus x squared minus f times g prime, which is just 2x, all divided by 1 plus x squared equals 1 plus x squared minus 2x squared over 1 plus x squared is 1 minus x squared over 1 plus x squared. Oh, and I forgot to square my denominator. Whoops. Sorry. If you were at home wondering, why didn't you do that? I just forgot. Sorry. All right, so 1 minus x squared over 1 plus x squared quantity squared. In order to use the first derivative test, we're going to look for values where either the first derivative is equal to 0 or does not exist. F prime of x equals 0 when 1 minus x squared equals 0. And that happens when x squared equals 1. Remember, that means that x can be plus or minus 1. Now, f prime of x does not exist. Well, that happens when 1 plus x squared equals 0. And that means x squared equals -1, which can never happen. So you have these two critical numbers at plus or minus 1. And we'll go ahead and use sign analysis with these two critical numbers to determine where we might possibly have local extrema. So let's go ahead and put our number line together. We're going to look at -1 and +1. First, we'll use the first derivative. So this is a good review of what we did last time. F prime of, let's say, -2, 0, +2. And then you can go ahead if you'd like and put these into your calculator. So I'm going to enter the first derivative into my calculator. The first derivative is parentheses 1 minus x squared, parenthesis, divided by 1 plus x squared, parenthesis, squared. That is my first derivative, right? Yes. Okay. Excellent. Now I can go ahead and go to my table. I've got -2, 0, +2, which is going to be negative, positive, negative. So this is negative 0.12, 1, and negative 0.12. So less than 0, greater than 0, less than 0. So if I was trying to find local extrema, I'd say, okay, less than 0 means we're decreasing, greater than 0 means I'm increasing, less than 0 means I'm decreasing. The first derivative test would say that I have a minimum at -1, f of -1, and a maximum at 1 and f of 1. To do this with the second derivative test, you would basically stop at this point where you found the first derivative, and then all of this stuff wouldn't be written. You would go straight into the second derivative test. Or I'm sorry, and straight into the second derivative, and then use the second derivative test with your critical number. So actually, maybe I should restate that. You would not have done the sign analysis, but you would still have to find the critical numbers. So for f double prime, I'm going to take this derivative, f prime g minus so let's see, f prime g minus f, and then g prime needs the chain rule, all divided by g squared. And then you'll go through. You should be pretty good with the quotient rule by now. And get rid of one factor of 1 plus x squared and simplify. So you'll have -2x and then minus 2x cubed. And then we're going to take 4x and distribute it in here with a negative. So this will be -4x. And now a negative times a negative is a positive. So I'm taking a positive and then 4x cubed divided by 1 plus x squared, quantity cubed. And then we'll simplify that. So we have f double prime of x equals positive 2x cubed minus 6x divided by 1 plus x squared, quantity cubed. So what you're going to do to use the second derivative test is you're going to find these same conclusions, we hope, by evaluating the second derivative at the critical numbers, which we found right here. So you're still using the critical numbers. You're just not doing sign analysis on them. You're actually just evaluating the second derivative at those values. Now, we already have those values in our, we already have this, actually, we have the first derivative in our calculator, not the second. So we're going to have to enter that. So you're going to take f double prime and evaluate it at the first and the second critical number. And you're going to look at the sign of the second derivatives evaluated at your critical numbers. If the sign is less than 0, then you have a relative max there. If it's greater than 0, you have a relative min. So again, you can just input this straight into the function if you want. If you trust yourself more with the calculator, then do it that way. I'll just do the calculator because I think it's really good for us all to see how this is entered all the time with these rational functions. So there's your numerator. In the denominator, you have 1 plus x squared, quantity cubed. And then we'll evaluate these in our table at -1 and 1. At -1, you get y equals 1/2. And at +1, you get -1/2. 1/2 is greater than 0, -1/2 is less than 0. Therefore, this critical number results in a relative minimum. and the second one results in a relative maximum. Now, notice that that's the same conclusion we came up with here when we did sign analysis. Now, we're going to go ahead and just put some points on here so you at least have these actual extreme values. So we can say that the relative min is at -1, f of -1, and the relative max is at 1, f of 1. And then you can go ahead and pop these into the function if you want. The function's actually pretty straightforward. Note that whether you're entering x equals positive or -1, you're squaring it. So the denominator is going to be the same in each case. Or you could just put this into your calculator. But f of -1 would just be -1 over 1 plus 1. So it would be -1 over 2. And then f of 1 is just going to be 1 over 2. So it's a half. So these would be the values for your relative mins and maxes on the graph, just found in two different ways. So the second derivative test is just an alternative to the first derivative test for finding extrema. It doesn't tell you anything necessarily about concavity. It's just a test to determine whether a critical number results in a relative maximum or a relative minimum. Now, again, it's kind of up to you how you want to use the second derivative test. I'll probably ask you a question on your test just to verify that you understand how to use it and what it is. But most of the time, I think it's probably easier to use sign analysis, but maybe that depends on the type of function you have. Maybe for a polynomial function, it's easier to use the second derivative test because it's easier to find the second derivative. But I mean, look at all the work that we put into finding the second derivative here. It was not like super easy. So using the second derivative test on a function where the second derivative is hard to find, you might want to think like, well, maybe I should just go back and use the sign analysis on the first derivative test. Regardless, the conclusions are the same. It's just a different way of finding the same thing. So that is one application of the second derivative. The last thing we're going to do in this section is sketch some curves based on some information. Now, what I love about this is that it kind of leads us into what we're going to be doing in the next section. In 4.3, we're really going to be focusing on how do we graph a function just by looking at its first derivative, looking at its second derivative, and using everything we know about algebra to create a really nice graph, thinking about where it increases, where it decreases, where it's concave up, where it's concave down, where's the max, where's the min. There's so much we can tell now about a function just by looking at the graph and at the function and its derivatives. So we're going to do two sketches here as the last thing we do here today. The first one is giving us some information first about, for instance, this value on the graph. It's saying that when x is 1, y is 2. Remember from chapter 2 and from algebra, this is just an algebra concept. So it's just giving you a point on the graph. So f of 1 is 2. That point on the graph is right here. So we're going to start putting this information down as we can. It also says f prime of 1 is 0. That means the slope of the tangent line at x equals 1 is 0. That means the tangent line is horizontal at x equals 1. So that must mean that we have some sort of a maximum or a minimum value. You can sketch it if you want. It's not technically part of your graph, but that means that this is going to be some sort of extreme value, probably. Either max or min. Now, it could always be one of those places where the graph levels off and keeps going in either direction. So we're going to use the rest of the information to determine if that's true. The derivative or the slopes are positive from -infinity to 1 Okay, so that means that the slopes of the tangent lines are increasing. It must be the case that f is increasing up to x equals 1. And then we know that the slopes are decreasing on 1 to infinity, or I could say that f is decreasing from 1 to infinity because the slopes of the tangent lines are negative. Maybe I should say it that way. Don't want to get that confused with the concave up and down business. So this just means that f is increasing on the interval from negative infinity to 1, and f is decreasing on the interval from 1 to infinity. So we know that we've got this behavior where f is increasing to the left of 1, decreasing to the right of 1, and we know that f double prime is less than 0 on the whole entire domain, which means that f is concave down on its domain. We can use all of this information now to just sketch what this graph must look like here. So you don't have to make it perfect. I didn't give you a function, so you can't actually plug in any values to determine any points, but you can just draw a general graph of what you think is happening. So we already used this, the first fact. The second fact we know, and now we know we have a max because we're increasing to the left, decreasing on the right. We're concave down the whole time. You can make your graph look like this-ish. Remember, it's just an approximate. You don't have any actual values you can plug in for x to find y, but this is about what your graph looks like. Isn't that cool? I'm going to definitely put something like this on your test. For the next one, this one's a little bit trickier. We have a little bit more information that we're dealing with here. But we do know f of -4 is 0, so that gives us a point at -4, 0. And f of 0 is 0. So I have another point. These are x-intercepts. We're going to be talking more about those next time when we talk about curve sketching. You learned all about them in algebra, but I'm going to go ahead and plot them. -4, 0, and 0, 0. Our graph is crossing through the x-axis at those points. And I know that f prime of -3 is 0. So that means that I have some sort of extreme value here, or at least I know I have a horizontal tangent line. When x is equal to -3. Now, let's see. I don't really have a whole lot of information about the y value, though. All I know is that somewhere when x equals -3, we have a horizontal tangent line, but we don't know. Like, is it down here? Is it up there? We don't know. So we need to use the rest of this information to determine that. Well, luckily we know that from -infinity up to -3, your graph of f is increasing. So from -infinity up to -3, the graph is increasing. Well, the only way that it can do that is by coming up from -infinity and going through this x-intercept and somehow moving towards x equals -3. That's the only way that can happen. So we know something like this is happening. And we know that from -3 to +infinity, f is decreasing. But it's a little bit harder to say what's happening there because we also know that we have to go through this point. So we know that somewhere we have a horizontal tangent line. Maybe it happens here. We don't know. That's from that second piece of information. We know the graph is decreasing. So it's got to be going through this point somewhere, but we don't know how it's decreasing. So we have information, though, about the concavity. We know that it's concave down. From -infinity to -2, and from 0 to infinity. So if it's going to be concave down up from -infinity to -2, we at least have some sort of an idea about what it's doing on those intervals, and it's concave up from -2 to infinity. So, I'm sorry, -2 to 0, it's concave up. And I know I have this point here at 0. So somewhere in between -2 and 0, it's concave up cup. So something is happening. We don't exactly know what, but you are going to just attempt to make a graph that matches this data. So this is going to be your cup, concave up, and concave down happened all the way up to -2. Now, again, this y value here at -3, we don't exactly know where it is. Put it somewhere where it makes sense. Maybe you have it a little bit higher, slightly lower, but it can't be too low. Otherwise, it can't be concave down up to that point, kind of depending, I guess, on where you put this value. Again, this was just a guess. We don't actually have a value there to graph. So we put it there because it matched the information, but it doesn't have to be exactly right there. Okay, so concave down, it switches. This is your POI, point of inflection. And then it changes its concavity. It becomes concave up. And then all the way from 0 to infinity, it's going to be concave down again. And we also know that it's decreasing from -3 to infinity, which we have. So it's just that the concavity is going to change. So here we are concave down, concave up in the middle. If you want to think about it, we just have this section here where we're concave up and then concave down. So we had the point of inflection here, and then this would be another point of inflection where the concavity changes from up to down. This is a tricky example. Spend some time looking at this. Like I said, there's some stuff that we kind of had to guess around here, but this graph matches the information. It's just that we couldn't get everything exactly where it was supposed to be. These 2 points are exact on your x-intercepts. These 2 are arbitrary, but they only have so much wiggle room where they can move. Your graph must be pointing down in both directions. So this one's a little tricky, but you'll see a couple of these in your homework. I wish that there were more, but there weren't a whole lot of them to assign. All right, that is all. I hope you enjoyed your discussion of the second derivative today. You'll have so much fun taking second derivatives of quotient rules all day long. It'd be great. Some of you really enjoy that, I know. But that's all. Next time we'll talk about curve sketching, and we'll put everything together to sketch some curves, which is one of my favorite things. So expect a lot of enthusiasm because I'm really excited about it. Totally excited. Pumped. So you have something to look forward to. Enjoy the rest of your day.